Hi everybody, so we're going to start talking about chapter 2, which is about systems of linear equations. Okay, so the first thing we want to do is say what the solution to a system of equations looks like. Okay, so this is something we should know. Okay, so a solution to a system of linear equations, or really any system of equations, is an ordered pair x, y that when you substitute, right, or plug it in, gives a true statement for all equations in the system, okay? So for a single linear equation, we know that this is true, right? You plug it in, it should give you a true statement like 2 equals 2, okay? For a system of equations, that has to be true for each equation in the system. Okay, all of them. It can't be true for one and false for the other. Okay, so let's learn some new vocabulary surrounding this. Okay, so if your system has a solution, any solution at all, it's called consistent. Okay, the opposite of that okay, we would say if a system has no solution, it's called inconsistent. Okay, so those two are opposites. If there is a solution, it's consistent. If there's no solutions, then it's inconsistent. Okay, you'll notice that this doesn't say how many solutions there are. There could be one, there could be many, just as long as there are any at all. Okay, and the other pair of words that we're going to talk about is independent and dependent. Okay, so if each equation in the system is necessary, or if each one is bringing unique information, then we call that system independent. Okay, so the opposite of that is if one or more okay, so if you could remove one or more of the equation and it wouldn't change the solutions at all, right? Then we would say this is dependent. Okay. So as we go through, we'll talk about these four words: consistent, inconsistent, independent, and dependent, okay? But that is just the definition of what they mean, okay? All right, so let's look at our first example, which is a graph, okay? So this says two linear equations, L1 and L2, are graphed below, okay? So here they are. And then we're going to answer some questions about that. Okay, so part A says, which points are solutions to equation 1? Okay, let me try to move this so we can see the questions in the graph. There we go. Okay, so you can see that here it says the green line is equation 1. Okay, so we're going to answer what points on here are solutions to equation 1, which is represented by the green line. Okay, now of course you guys remember that every point on this line is a solution to its corresponding equation. Okay, so we're going to list all of the points that fall on this line. So that would be A, C, and D. Okay, then part B asks, which points are solutions to equation 2? Okay, so equation 2 is represented by this orange line. Okay, so we're going to list all the points that fall on that line, right? Because that line contains all of the solutions for that equation. Okay, so that's going to be point B and point D. Okay, now it says, which points are solutions to the system? Okay, now a solution to the system would be a solution to each equation. Okay, so this should be something that is a solution to both equation 1 and equation 2. So if you look, there's only one point that is in common between them. That's point D. Okay, and if you look at the graph, you can see that this is the point of intersection. Okay. So I hope you remember from your Algebra 1 class that the point of intersection will be the solution to the system. Okay, now let's answer a question about those vocab words. Is the system consistent or inconsistent? Okay, well there is a solution. We found it. It's point D. Okay, also we could give the ordered pair for this because we know it is -2, 1. Okay, certainly we can determine that visually. Okay, so is the solution consistent or inconsistent? Well, it has a solution, so that means it's consistent. Okay, remember this means has a solution. Okay, and we know that because we found that solution in part C. Okay, now dependent or independent. Well, if you look at this graph, you can see that these two lines are independent of one another, right? They're not the same. Okay, that's what two lines being independent visually looks like, is that there are two different lines. Okay, so we would say that this is independent. Okay, and this is because there are two different, right, different or independent lines. Okay, so we would say that this system is consistent and independent. Okay, let's look at an example of using a graph to solve. Okay. Okay, so it says solve graphically, right, or using a graph. And the system that we're interested in is okay. So the first thing we're going to do is make a graph here. Okay, so I'm going to make a graph of these two lines. Okay, and I'm going to graph them here on the same plane. Okay, so first I'm going to graph x plus 2y equals 4. Okay, and I'm just going to do this using the intercept method. Okay, so this is my L1. Okay, right, I'm looking to use the intercept method. Okay, so if I plug in 0 for x, I'll get that y is 2. If I plug in 0 for y, I'll get that x is 4. Okay, so I'm going to plot those 2 points. I'm actually going to go by 2's here because I know I'm going to have to plot something like 12. Okay, so I'm going to go 0, 2, and then 4, 0. Okay. Okay. So that's my first graph. Then I'm going to look at my second graph, L2. Okay, and I'm going to graph this using the slope-intercept method. Okay, so this again was from L1. That's the intercept method for graphing. Okay, and now I'm going to use the slope-intercept method to graph L2. Okay, you can graph using whatever method you prefer. This is in standard form, so I just graph using the intercept method. This is in slope-intercept, so I'm going to graph using the slope-intercept method. So my slope here is 3, and my y-intercept is going to be 0, negative 12. This wasn't very smart, was it? I was thinking of positive 12 for some reason. Okay, let me grab another piece of graph paper. Okay, so I'm just going to quickly redraw this. Okay, so again, I'm going to go by 2's. So this is going to be 2 here, and then I'm going to go by 1's here. Okay. All right. So for my first graph, again, I had the points 0, 2, and 4, 0. Okay, so 0, 2, and then 4, 0. Okay, and then I'm going to graph my line. Okay, so this is my equation L1. Okay, then for my equation L2, I had that my y-intercept was 0, negative 12, so I'm going to go here. Okay, and then my slope was 3 over 1, which I'll remind you guys is the same as 6 over 2. Okay, and I'm doing this because my graph goes by 2's. I don't really want to do 3. Okay, so I'm going to go up 6, 2, 4, 6, and then over 2, 1, 2. Okay, now you can see that this is the same as if I would have gone up 1 and like 3, right, which is 1.5. Okay, and then over 1. So this would be the point that I marked if I did that. Okay, and you can see they are all lined up. Okay, so there's my line there. Okay, so now when we look at these, we can see this point of intersection, okay, which is the point 4, 0. Okay, so we're going to give our solution, right, where it says solve graphically. Our answer would be 4, 0, okay, or you could format this like x equals 4, y equals 0. Okay, so either one of these two formats is an acceptable answer. Now, if you're solving graphically and you're not sure if your answer is correct because you're estimating from a graph, okay, you can always plug in your values to check, right? 4 plus 0 equals 4, true, right? 0 equals 12 minus 12, true. Okay, so you can always plug them in to check your solution algebraically. All right, so let's see part B of that example. Oh, wait. Let's look at this and talk about consistent and inconsistent, dependent and independent. Okay, so here we can see that there is a solution, so we would say this is consistent. Okay, and then we can see we have two totally independent lines, so we would say this is independent. Okay. All right, so now let's look at part B. Okay, so we have x minus 2y equals 6. Okay, and then y equals 1/2 x minus 3. Okay, so I'm going to graph these two. Okay, so again, I'm going to make my first one be my L1. I'm going to do that in green, and then I'll make the second one L2 and do that in orange. Okay, so I'm just going to do this using the intercept method. Okay, so if I let x be 0, then I'm going to have y is -3. If I let y be 0, then I'm going to have x is 6. Okay, so now I can kind of see what size my graph needs to be. Okay, now I'm just going to go by ones. So I'm going to do 0, -3. Okay, and then 6, 0. 6. Okay, and then I'm going to draw my line. Okay, now I'm going to look at my second equation, which is going to be L2. Okay, so I'm going to use the slope-intercept method. Okay, so my slope I can tell is 1/2. Okay, and my y-intercept is 0, -3. Okay, so I'm going to graph my point 0, -3. Okay, and then I'm going to go up 1 and over 2. Okay, and then I'm going to connect my points with a line. Okay, now before we even say what the solution is, let's talk about consistent, inconsistent, dependent, and independent. Okay, now if you're looking at this picture, it does look unusual, okay, but is there a point of intersection? Well, yeah, there's a ton of points of intersection. Okay, so this is consistent, right? There is a solution. In fact, there's a whole bunch. Okay, now are these two lines independent of one another? No, they're the same line, and that's exactly what it means, okay, for the system to be dependent. So this is a perfect example of a dependent system. Okay, now what are we going to say about the solutions? Okay, well, every point on this line is a solution because they're all on both lines because the lines are the same. Okay, so we would say that there are infinite solutions. Okay, all right, and that often goes along with dependent systems. You will see these two together a lot. Okay, let's look at the last part of this example, part C. Okay, so again, we're going to solve graphically because that's what's in the directions. Okay, so my first one, L1. Okay, again, because it's in standard form, I'm just going to use the intercept method. Okay, so for the y-intercept, if I let x equal 0, I'm going to get 5. For the x-intercept, if I let y equal 0, I'm going to get 5. Okay, So let me graph my points here. Okay, so I have the point 0.05 and the point 0.50. Okay, and I'm going to connect these two. Okay, then I'm going to look at my other equation. Okay, and I'm going to use the same method actually. Okay, so if my x value is 0, okay, then my y value is going to be -2. If my y value is 0, then my x value is -2. Okay, so 0, -2, and -2, 0. Okay. Now, if we look at these lines, one thing that you might notice about these two lines is that these are parallel. Okay. So what does that mean about the point of intersection? Is there a point of intersection? No. Okay. So what that means for us, right, since the solution is the point of intersection and there isn't one, that would mean there's no solution. Okay. Now let's talk about consistent, inconsistent, dependent, and independent. Okay. If there's no solution, this is going to be inconsistent. Okay, no solution means inconsistent. These are exactly the same. Okay, then is it independent or dependent? So if you look at these two lines, they are independent of one another. So this is independent. Okay, so this is inconsistent and independent. Okay, so that's really all of the review from this section. Hopefully this refreshes your memory about how to solve graphically, and in the next section we'll talk more about how to solve it algebraically. I'll see you guys soon.